In this video, we will discuss the problem M coloring. The problem says that we have been given an undirected graph and we have been given an integer M. Our task is to determine if we can color the graph with at most M different colors such that no two adjacent vertices of the graph are having the same color. And here color of a graph means that assigning color to all the vertices, we have to print one, that is we have to return true if it is possible, otherwise we have to return 0 or false if it is not possible. So let us quickly check the sample test case to get better understanding of this problem. So let's say if the sample test case, okay, suppose we have been given this graph. So suppose we have been given the number of nodes as 4 and we have been given the edges like this. So it says that 0 is connected to 1. So let's say let's connect 0 with 1. Okay, then let's connect 1 with 2. After that 2 is connected with 3. Then 3 is connected with 0. And after this 0 is connected with 2 as well. So if these are the connections that we have made, so we have to color it like M value is given as 3. So we have to color this graph using at most 3 different colors. So let's say if we color this 0 node with the color as 1, okay, after this suppose that we color the node 3 with the color as 2. After this since 0 is adjacent to 1, so when we color the node 1 with color 2 as well, okay, then after that if suppose that we color the node 2 with color 1, so in this case it will not be possible because 0 and 2 are adjacent and they will have the same color. So since I have 3 different colors, so if I try to color it with 2, so I cannot color it because the adjacent for 2, the adjacent is 3 and 1, it will have the same color, so I cannot color it. So in that case I will try to color it, let's say with 3. So can I color it with the color 3? Yes, because now 1 is like 0 is having a different color, then 2, 3 and 1 are also having different color. So this means that it is possible and I can return a true from here. Now in this problem, if I have to consider the second test case as well, so let's quickly check that out. So 0 is connected to 1, 1 is connected to 2 and 2 is connected to 0. So let's say another graph was given where 0 was there, 0 was connected with 1, then 1 was connected with 2 and then 2 was connected with 0, and suppose that I was given M is equal to 2, okay, in this case. So if I try to color them now, so I can easily observe that suppose I color 0 with the color as 1, okay, after that if I color 1 with the color as 2, in that case can I color 2 with the can I color the node 2 with color 1? No, I cannot. Why I cannot? Because it will not be possible, because the adjacent cells 0 and 2 will, adjacent nodes 0 and 2 will have the same color. Can I color the node 2 with the value as 2? No, because in this case you can see 1 and 2 will have the same color. So you can see that since I had only 2 different colors, so it will not be possible for me to color this graph. So in this case I will return a false from here. That is what the problem statement says. Now if we have to think, so basically what we can try to do, if you have to color the nodes of the graph, so we can think of doing it using all possible ways, right? The first thing that comes to our mind is all possible ways, and when we think about all possible ways, then the approach will be nothing but recursive in nature, right? We can use recursion. When we think of all possible ways, it is nothing but recursion first of all. And another thing that we need to consider is that suppose like when we have to color, so if we are trying recursion, that is all possible ways, so this basically indicates that we will try to paint every node with all the colors, right, with all possible colors, right, with all possible colors from 1 to M. Okay, this is another observation that we can have. We will try to print every node with all possible colors from 1 to M. Now let's move forward with this question and try to see how we'll be doing it recursively. So suppose we are at 0, right? Suppose we are at the node 0. So suppose we call the recursion for 0. When we call the recursion for 0, so we have several choices for it. Either we can color it the node 0 with color 1, we can color it with 2, or we can color it with 3, because M value is 3 here, so we can color it with any color between 1 to 3. But first of all, let's try and color it with the color 1, okay? So let us see that what will happen when we color the node 0 with the color as 1. So let's say I call it for the 0th node, I try to color it with the color as 1, okay? Then what will happen? I'll move to the, like I will try to see that, okay, if I color it the node 0 with 1, Then what will happen? After this, what we will do is we'll move simply to the node 2, right? So node 1, so that is this node. Now when we move to this node, then what we will try to do is, let's say if I try to color it with the color as 1, so can I color it with the color as 1? No, I cannot. Why I cannot? Because if I mark the color of the node 1 as 1, in that case it will not be possible, because adjacent 0 and 1 are adjacent to each other. So in that case it is not at all possible. So in this case, what I will try to do is, I'll simply try and backtrack, right? I'll backtrack because 1 from 1 it was not possible. But let's say if I try to color 1 with the color as 2, okay? So in this case, when I try to color it with the color 2, so it is actually possible. Why it is possible? Because here I can see that no adjacent nodes are having the same color, right? If one has the color as 2, so it seems to be fine. Then I will call the recursion for here for the node 2, right? When I call the recursion for node 2, then first of all I'll try to color the color as 1. So can I color it with the color as 1? No, I cannot. Why? Because if I color it with the color as 1, then 0 and 2 will have the same color, so it will be trouble. Now if I cannot color it with the color as 1, so I'll try to color it with the color as 2. So if I try to color 2 with the color as 2, in that case it 0, 1 and 2 will have the same adjacent color. So in that case I cannot color it with 2 as well. So I'll try to color it with 3. So let's say if I try to color it with the color as 3. So now if I color it with 3, so it's actually valid, because if I'll see, so 0 and 2 have like different colors, and 1 and 2 also have different colors. So I can color it with the color as 3. Then what I will do is, after coloring the node 2 with the color 3, I'll move to the to the third node, to the node with the value as 3. When I move to this node, so I will first of all try to color it with the color as 1. So can I color it with the color as 1? No, I cannot, because 0 and 3 are adjacent and they will have the same color. Then I will try to do what? I'll try to color it with the color as 0. Color it with the color as 2. So can I color it with 2? Yes, because if I color it with 2, in that case what happens? I can see that no adjacent cells have the same color, because 0, like 3 is connected with 2 and 0. So 0 is having the color as 1 and 2 is having the color as 3. So in that case I can say that 3 can be colored with the color as 2. So I'll color it with 2 and I'll recursively call for the next node. So the next node will be value 4. But actually we have reached the end of our case, because you can see when we hit n is equal to 4, when we hit 4, so that is the total number of nodes that we had. So 0 is colored, 1 is colored, 2 is colored, 3 is colored, and now I reached the end of the graph. All the nodes are colored. So in that case I can simply return a true from it. So I'll return a true from here, and this part will return me a true. After this segment will also return me a true, and this segment will also return me a true, because it is possible. If it was not possible, then we would have backtracked and changed the color to back to 0, and then we would have tried to color it again with a different color. And if after trying all the possibilities, if it was not possible, then we would have returned a false. So let's quickly check this for the other case as well. So suppose if the graph was 0, okay, 0 was connected to 1, and then 1 was connected to 2, and 2 was connected to 0. If this was the graph that we had, and here the m value was given to us as 2, so can we color it with two different colors? So first of all, if I call the recursion, so recursion of 0 if I call, so either I can color it with color 1 or 2, but first of all let's check it whether I can color it with 1 or not, because that will be called first. So after that, when I call recursively for 1, so can I color 1 with the color as 1? No, because 0 is already colored with 1, so I cannot color 1 with the color as 1. So I'll try to color it with the color as 2. So can I color it with the color as 2? Yes, I can color it, because no adjacent node is having the same color. Then I'll move to the next node. So I'll move to the next node, that is nothing but 2. So when I move to 2, so I'll try to color 2 with the color as 1. If I try to color 2 with the color as 1, in that case what happens? In that case I can simply say that it is not possible, because if I color 2 with the color as 1, in that case 0 and 2 have the same adjacent color. So in that case I will return a false from there, right? I'll move back. Can I color the node 2 with the value as 2, with the color as 2? No, I cannot, because in this case 1 and 2 will have the same color and this will not be possible. But in this case, if it is not possible, so now what I'll try to do is I'll try to backtrack from it. Okay, when I backtrack, so I can observe that I had this part as well. Like either I color it, like I can see that I tried to color it with 1, but that was not possible, so I colored it with 2. Now these calls are exhausted. Now I'll move up. So I tried to color the node 0 with the color as 1. Now I'll try to color it with the color as 2. Okay, so I can try at most two different colors. So now I'll try to color it with 2. Okay, So when I color the node 1 with the color as 2, node 0 with the color as 2, starting node, then after that I'll call the recursion for 1, right? I'll call it for 1. When I call it for 1, so can I color it with 1? Yes, I can. So suppose that I color it with 1, okay? Then what happens? I'll call the recursion and I'll call it for 2. So the node 2 for this node. Can I color it with the color as 1? No, I cannot, because in that case what happens is 0 like 2, the node 2 has the same color as the node number 1, node with a value 1. So can I color the node 2 with the color as 2? No, I cannot, because 0, the node 0 and 2 are connected, they are adjacent to each other and they will have the same color. So in that case it is also not possible. So I'll simply backtrack, and while I'm backtracking, so I'll mark the color as 0 so that I can change the color later on. After this, when I will see here, so these two possibilities are explored, then I'll move back from here, and then I will try to color, like I tried to color the node 1 with the color as 1. Now I'll try to color it with the color as 2. Can I color it with the color as 2? No, definitely I cannot. Why I cannot? Because if you will simply observe here, then I can see that 0 and 1 will have the same color, so that's not possible. So all the opportunities are explored, then I'll move back. While I'm moving back, so I can return a false, because I have explored all the opportunities and it was not possible. So ultimately for this case, I'll return a false. So this is how we'll be doing it. This is nothing but recursion, in which we'll also be using backtracking process, so that whenever we use a particular color and if we do not get it true, then what we will do is we'll mark the color as 0 again, so that we can update the color later on. And we'll also keep a check for a particular node. Let's say we want to color 1 with the color as 2, so we'll try to check in the all the directions, all the adjacent cells are having the different color or not. If they have the same color, then it will not be possible. So we'll have a possible function as well. Now if you think about the time complexity of the approach that we are thinking of, so in that case what will happen here is, you can understand that since there are n nodes, and like there are n nodes that are there, and m different colors are there, right? So we are trying to do what? We are trying to color, like we are trying to apply, like for a particular color, we are trying to have all the nodes, right? So in that case, we are like, how many opportunities we have? So for one node we have m different colors that we can apply to it. So for second node also we have m different colors that we can apply to it, right? So for every node we have m choices, right? M different choices, right? So in this case, if we'll multiply m into m into m n times, so that will be nothing but m to the power n. So that is why the time complexity of this code, the approach will be order of n to the m to the power n, but the constraints will be small, so the problem solution will get accepted, and the space complexity will also be order of n. Why? Because we are using the color array for storing the color of all the nodes, right? So let's try and write the code for this approach quickly and see what will happen further. So what we'll be doing here is, we'll simply declare a recursive function here. First of all, we'll have a color array. So what we will be doing is, we'll have the color like vector int, and we can mark the color. We can use a list in Java. So we'll have n, like for all the n nodes we'll initially mark them as 0. Then what we'll do is, we'll return whatever the recursive function will return from to us, we'll return that. So we'll pass the graph. The graph is 2D in nature. You can see 101 101. It is nothing but an adjacency matrix here, because if it says here, like it will denote that whether two people are connected to each other or not. Okay, so the graph will tell you this thing. After that, you will pass the n, that is the number of nodes. You will pass m, and you will pass the initial color, let's say like 0, and then you will pass the color that you are, like color array that you have taken. After this part is done, so what you will do is, you will write the recursive function. So recursive function will be boolean in nature, so we'll write the recursive function here. First of all, we'll pass the graph, so we'll pass bool, then graph, for 101 that is the nodes, right? Then I'll pass int n, then I'll pass int m as well, that is the n value and the m different colors that I can use. And after this, what I'll pass is, I'll pass the initially the index that I'm at. So index I'll pass, initially I'm at 0th index, right? So I'll try to color the 0th node. Basically index represents the node. And I'll also pass the color array. I'll pass the color array by address, so that any change I make to it is reflected in all the recursive calls. So if it happens that I is greater equal to n, okay, if the index, like if the current index, if the index becomes I is greater equal to n, if the recursive calls are done for n is, like if I do the recursion and if I reach, let's say if they were only, if n was equal to 5 and I reach 5, if I index also represents 5, in that case I have reached the fifth node of the graph as well. So in that case, like if I have traversed all the nodes and I was able to color them, then that is only when I'll reach the end. So in that case I can return a true from it, indicating that okay, it is possible. Otherwise what I will try to do is, I'll try to say that okay, what are the color options I'll have. So initially I'll mark the color as 1. So from 1 till m, right? So I have m different options that I have. So I'll do what? I'll do color plus plus. So from 1 to m, I'll try to apply all the possible colors. So I'll check that if it is possible, right? If it is possible to take the current color that I'm planning to take, because if some adjacent node is already colored with that color, so I'll not use it. So I'll write a possible function to check that if any of the adjacent nodes of the current node is having the same color or not. So I'll pass the index here, okay, then I'll pass the color. I will also pass the graph here, and I'll pass m and the color array. Okay, so if this returns me a true, right? If this returns me, let's say if like this function will check whether it is possible to color or not. So let's write it as well. So what we'll be doing here is, we'll simply denote that bool is possible. We'll write bool is possible, and then we'll have the int index, and we'll have the color, and after this we'll have the bool graph, not the bool graph, we'll have the like, yes, we have been given the graph in bool only. We'll have the bool graph, and the graph will have dimensions 101 101. After this we'll also pass the n value here that we have passed, and we'll pass the color as well. So after passing these values, what we will try to check is, we'll try to check for all the n nodes, we'll try to check if it has a connection with the current node or not. So I starts from 0, I is lesser than n, then I plus plus is what we will do. Okay, so I need to mark it like this, and what we will be doing is, we'll say that if the graph of index I is equal to 1, if it's 1, then that means that the uh, current node is connected with this particular ith node. So if it is connected, so in that case I need to check the color. So if it happens, if the color that I have currently chosen, right, if the color that I have currently chosen is equal to the color of the ith node, in that case what I will do is, I'll simply need to return a 0. Like I need to return what? I need to return a false, you can say. Why I need to return false? Because that will not be possible for us, because if the adjacent node is already colored with the same color, then in that case it is not possible, so I'll not color it. Otherwise, if I check for all the cases and I never return a false, if I check for all the nodes and no node is having the same color, so I'll never go to this if. So in that case, after the for loop is over, so I'll return a true, indicating that okay, it is possible. So if this function returns me a true, if this function returns me a true, in that case what I need to check here is, I need to check that whether or not, like, I first of all I need to color it with the same color. So I'll color the current node, that is the current node in like, which is I'm indicating with index. So I'll color it with the color that I have chosen. Okay, then after this what we'll do is, we'll pass this function, right? So we'll pass this recursive function, and we'll pass the graph here first of all, then we'll pass n, we'll pass m, we'll pass the index as well, and we'll pass the color array along with it for the next call. Okay, if it returns us, like, let's suppose that it we call for it and it returns us a true. If it returns us a true, so if it indicates that it is actually possible, in that case if it indicates that, suppose that we called, right? So suppose we were calling from here. So if it indicated that, if we called, okay, if we called that, okay, this node, for every recursive call we called one by one, and it the final call returns a true, then we'll return true from every call, because we don't need to check any further, right? So in that case we'll simply return nothing but a true. Otherwise what we will do is, in the else case, we can say that what we'll do is, we'll mark the color of the current node as 0, because this is nothing but the backtracking process. Because if we were not able to color it, like if we were not able to get this graph where all the adjacent nodes were different, so in that case, in the else part, we'll again color it back to 0. That is we'll remove all the colors, right? We'll remove the current color. Why? Because we will again like try to have the all various possibilities. So that this is nothing but the backtracking process. Let's try and compile this code. Okay, so we are getting a segmentation fault. Let's quickly check where we are making a mistake. So what we are doing here is we are having the graph first of all. So when we have this graph, so first of all we are passing n and we are passing 0. The color initially is 0 for all. Then in the recursive function we are passing the graph, we are passing n, we are passing m, and we are passing the current node as 0, and we are passing the color array as well. Now what we are doing is we are writing a recursive function in which we are passing the graph, we are passing the int value, we are passing the m value, we are passing the index, and we are like we are also passing the color array, right? So if the index is greater equal to n, then we return a true simply. Okay, so if it happens that the like we'll start from color is equal to 1 until the color is less equal to m. Okay, after this part what we'll do is, if it is possible, right, if it is possible for the current index, for the current color and the current graph. Okay, I have not passed, I should have not passed m here, I should have passed n here, because what I was doing, I should have checked for all the n nodes, right? So for all the n nodes, so I was passing m here, so I should have passed m. Now I think it should get compiled. Let's try and see. Okay, so still we are getting an error. Let's try and check further. So what is the error here? So I'm passing n and I'm passing the color as well. So if it returns me a true, if it is valid, then we will color it, we'll color the current with the color. And if we'll pass the graph, I should have passed index plus 1 here as well, right? Now we'll try to check for the next node, right? For the next node, so that's why I'll pass index plus 1 for the next node. Like if we color 2, then we'll try to check for coloring 3. Okay, it gives us an answer as 1, so that means it's valid. Now let's try and compile this code to see if it works on the samples or not. Okay, it gives us a wrong answer here. Why does it gives us a wrong answer? Okay, let's try and debug it. So it says that I'll have the n, I'll have 0, I'll have the graph, I'll have n, m, 0, color. Okay, so what mistake have I done? So if it's a true, then I return a true here. So let's check here as well. Okay, so if I'm checking for validity, so if the ith graph like if the color like if I'm moving, so if I'm checking for is possible, so I'm passing the index, I'm passing the color, I'm passing the graph as well, I'm passing n, and I'm passing the color array as well. So I will start from 0, I will be lesser than n, I plus plus. So if the index of I is equal to 1, right? So if index I is equal to 1 graph, so in that case they are connected. So if the color of I is equal to color of like if the color is equal to color of I, if they have the same color, then I'll have to return a 0 from here, right? That is false. Otherwise I'll return a true. That means it's possible. So there's some mistake that we are making in this recursion only. So what mistake are we making? So let's check. So first of all, I'm passing the graph, I'm passing n, I'm passing m as well, I'm passing the index as well, I'm passing the color array as well. Okay, so if it happens that if I is greater equal to n, then I'll return a true. Otherwise I'll try to color. So for color will start from 1, color will be go till m, and if it's possible, right? Okay, so I was not returning a false in this function. So if it's not possible, then I should return a false as well. So the return type was missing. I think now it should get compiled. It works on the samples. Let's try and submit it to see what happens. So you can see that our solution was able to pass all the test cases. In case if you understood the explanation, make sure to comment down understood and like the video as well. Thank you.